Okay. So first off, and everybody can see my screen and everything.
Yeah.
Okay. So this is our last week. So let me talk about the final exam for a few minutes, and then we'll finish off the slide set. We might need to go a little quick with that, but because we don't have too much more to cover. So the final exam, some of you have asked like what kind of flexibility you'll have for it and things like that. So what I'm going to do, it's going to be online. Blackboard. It will be up before class on Wednesday, and you will have the option to do it during class, but it won't be due until midnight Sunday. All right, so I know some of you can't come to every class and you have other work obligations or whatever it is. So you will have class time on Wednesday to do the exam. But if that isn't compatible with your schedule, then you just have to complete it by midnight on Sunday. It has to be done in a single sitting. So once you start it, you got to finish it. You can't kind of stretch it out across, between Wednesday and Sunday. So maybe pick about a hour and a half block or so of time to be able to sit down and do it. It's closed book, closed note, closed friend, etc. So this should be your own thoughts, your own work. There will be 10 questions. At least one conversion question, possibly more. And what I mean by that is like the, convert binary to hexadecimal or something like that. Also dealing with sizes. So for instance, I could ask you, what is, or even speeds. So what is 215 kilobits in gigabytes, something like that. So these are things that all computer scientists should be comfortable with, the difference between bits and bytes, that jump by 8, and then the kilobits or kilobytes and megabytes and all that stuff, the scalar of 1024 up and down that chart. So all those things should be pretty common knowledge to you now and should be fairly free points. All right. Now what I'm going to do is I'm going to relatively quickly, hopefully, flip through our slides up to this point and kind of point out the topics that I think are kind of most important, that have the greatest chance of showing up on the exam. I'm going to do the effective, I haven't written the exam yet, but I'm effectively going to do the same thing that I do when I go and write the exam, is I go through the slides we've covered and I decide what is assessment worthy versus what isn't. I try not to ask trick questions. So, I'll try to give you an idea of how great of a chance something is of being on the exam and that kind of stuff. All right, so before I start doing that, are there any questions? Okie dokie. And I'll probably be finishing right around 9 or shortly after 9 today. I'm at home because my ride's picking me up at sometime shortly after 9. I'm picking up my new Tesla later on today. I sold my Explorer and I'm bought a Tesla Model Y. So today's my pick up and get rid of conversion day. All right. So let's go back here. All right, so this is cursory stuff, important, but I'm not going to probably ask anything, specifically about that slide. Certainly there could be something on there about the, as I look through this, and we'll hit it again here in a few minutes, just that difference in memory speeds, the concept of the closer to the CPU you get, the faster the memory. So understand the difference between a hardware register and system memory and the hard drive. I think that's the most important relationships. You start getting into the L1, L2 cache. I don't know how I'd ask the question about that stuff, but that's a lot more specialized. Like, how do you use that to give a little bit more performance? But that generic relationship between memory that's right on the CPU versus memory that's shared amongst your computer versus your hard drive or solid state drive, in terms of speed and the relationship between those, I think is pretty important. All right. And then even off this slide, again, we'll bump into it here in a little bit, just that relationship of decisions related to mobile computing compared to batteries. They can't just decide everything is about performance. They have to weigh it against battery life. All right. I probably won't ask specific questions about like hard drive technology or anything like that, especially since they don't really relate to our mobile device world. It was really more of background info for this idea that this is the slower part of your memory subsystems. So here's that chart I mentioned a few minutes ago. Definitely be able to do math problems related to this. If I give you something in kilobits and ask you how many kilobytes or how many gigabytes that is, you should be able to give me the equivalent in different values. So this chart should be, you can memorize it if you want, but it's a pretty easy mapping. Everything over on the right column is a scalar of 8 from the left column, and as you go up and down, it's 1024. So like, here's an example of a question I could ask. If I give you an internet connection speed or something like that, ask you, how fast is this in kilobytes? Then you should be able to do that math and tell me. Okay. So again, that relationship between, we've focused on CPU and that relationship with the system memory and the hard drive in here. How you think about a computer, I would say, is an important concept for us, but focusing on that aspect of the computer. More history stuff. Understand the nature of the CPU. I kind of reference it as a collection of magic tricks. The CPU knows how to do a whole bunch of little tiny things. I don't know if I'll ask a question specifically like to ask you to regurgitate that, but certainly as we look at like assembly code stuff, understand that each line of that code has a one-to-one relationship with the CPU on the Snapdragon chip or the A12 chip, whatever whatever RISC processor or ARM processor rather we were dealing with. But those are individual magic tricks that does something probably relatively small. And we're going to look at the how stacks and functions work some today. Okay. I would say it's fair game to ask something about flash memory, but I probably, that would be a filler question. So let's call it a 10% chance. All of our mobile devices operate off of flash memory now. And, we looked into the different technologies, but I'm not sure how important those different technologies really are to us. So I would have to get pretty desperate for a question, I would think, to ask something specific about that. Yeah, it's nothing there. Certainly understand the goals of mobile devices. Kind of, this slide, I would say, just having an understanding of it, whether I ask something specifically about this slide or it's knowledge that your answers to other questions is likely to pull from. Know what those different things mean. When you get a mobile device that has 128 gigs of storage, what does that mean? What does that let you do? As opposed to if it has 8 gigabytes of system RAM. What is that used for? So we're right back to that relationship between the CPU and the system memory and the hard drive. Even within that, I would throw out, I think there's maybe a decent chance that there'll be a question dealing with our discussion around the CPUs and why our modern mobile devices typically have CPUs with multiple cores where not all the cores are the same speed. Some cores are slower speed than other cores, and maybe ask you to explain why that is and what the advantage is, something like that. All right, nothing from here, more just interesting mobile truths. Again, nothing from here specifically. Not that I don't care about the specific details of, our flash storage stuff. It's interesting information, but not necessarily something to focus on when we're looking at the architecture of mobile devices. Again, that's really that relationship with CPU, system memory, and hard drive. There could be a question about a compiler in here. We'll probably actually put a button on that today. I'm going to be looking at some Android versus iOS examples, but understanding that, even though our focus isn't on the high level language in here, ultimately a high level language gets compiled down to ARM instructions for us. So understand that the nature of that and what's actually happening. Okay, this is all related to that idea. The concept of operating system based system calls, and we'll see that again today, but this is again the follow through of the compiler needs to know about the architecture. So are you doing this for the Snapdragon ARM processor, and then what operating system? Are we targeting Android? Are we targeting iOS? Because the output of that compiler will change even for the same high level language if we're working with a different core underneath the hood operating system that has different system calls, or at least system calls referenced differently. All right, so, and this is actually something related to what we'll look at here in a few minutes today, but, if you remember, this was our Hello World and i386 assembly. So this is Intel, but this is, pretty old assembly code that ultimately does Hello World. Notice that we have a couple of variables down here. We're remembering the length of Hello World, and we're remembering the string itself. And then in our actual code up here, what do? We stage a bunch of values into some hardware registers. So we're saying, here's how long it is. This is the message. Where do I want to write it to? And then this number 4 here deals with syswrite, the syswrite system call. Now, remember this number 4 here for a few minutes because we're going to be looking at the Android version of the same program. And you'll see I'm 98% certain it uses 4 as well because the core operating system under Android is Linux. Then we call the operating system here and it goes and grabs it says, what do you want to do from EAX? Then it says, here's my 3 parameters I need. And that's related to how function calls work. Which we'll also try to talk about today, probably fairly quickly since we've covered this stuff. I'm just trying to button up some things, and then we call upon the kernel, and the kernel goes and writes it to the screen. Then we come back in, we change what's in EAX. This is our directive to the operating system. Now we're doing system exit. Call upon the operating system, it jumps here, it says, you want to exit the program, no problem. I require 1 parameter. What's my error code? That's in EBX. And then it goes ahead and your program's over. So this is our hello world in i386 Linux assembly. And we're going to see this looks very similar to what Android-based hello world in Android assembly will look like for a Snapdragon processor. This I probably won't ask about what happens if you don't have a target OS. That's where you're targeting the BIOS and that stuff. And that's not really a reality today unless you're writing an operating system. So if we were talking about mobile operating systems, that might be an interesting concept. But in here, we're talking again about that relationship between the CPU, the system memory, and the hard drive over and over and over and over again. Okay, and this slide effectively says what I just said. So understand that we're talking about CPU, between CPU, system memory, and the hard drive. Our focus here is on mobile devices, so this is just kind of compared and contrasted them. If there was anything related to this, I already said it, was that idea that decisions related to mobile architecture have to take battery life into consideration. Okay. Details about specific registers, I'm probably not going to ask about. You should certainly know what registers are, but the fact that, you know, register 13 is used as a program pointer or something like that, I would say is unimportant, but do understand the nature of like the instruction pointer and that it points to the next the next instruction, or in ARM thing, it points to the next 2 instructions in the future. And then you do the math backwards as opposed to Intel-based assembly, which points to the next instruction. I don't think anything new from here other than what I've said already today. Certainly understand the concept of multiple cores. What advantage do they give you when you have more than one core? What does that let you accomplish? And then that goes hand in hand with that discussion about why do modern mobile devices tend to have higher performance and lower performance cores? What problem are they trying to solve with that? Comparison of the early mobile OSs won't be something I'm going to test you on. Although we can see some of the, like this slide right here does basically show you how early Android just took a desktop Linux operating system and didn't take a lot of those considerations that we've discussed about mobile stuff into consideration. And that's why they had bad battery life and things like that. And they had, you know, support for a lot of things that iOS didn't necessarily have support for, because iOS was written specifically for a mobile device in mind, where Android was just a port of Linux to run on a mobile device and had a bunch of really great stuff that just drained your battery. So that's effectively what this slide says. Yeah, I would say nothing from here. All right, certainly now we're starting getting into technical things, certainly understand binary, hexadecimal, octal, the conversion between those things. I mean, you really should be able to convert between any bases since the patterns are the same. But, you know, if we're focusing on what are the common things we might deal with, it's going to be decimal because we're human, binary because we're talking to computers, and then octal and hexadecimal because those have convenient representations in binary, where the entire octal octet space can be represented in 3 bits and the entire hexadecimal hextet space can be represented in 4 bits. So that's what this slide says. There's our octet values, there's our hextet values. Then we talked about what the next popular base might be, which would be base 32, because its entire space can be represented in 5 bits. So all this would be fair game. That's more of an operating system slide. Certainly understand the nature of numbers. I know that seems like a kind of a stupid question, but you know that numbers are representative of an idea. Sometimes we're using numbers to do math, but sometimes we're using numbers for other things. A couple minutes ago in the assembly program, we saw numbers related to the sys-write system call, for example. That was just the number 4, and it didn't have any math relationship. It was just, it mapped to this idea of, oh, this is the sys-write system call. All right, so because we had some discussions about what if we have a 16-bit register and we want to hold 2 different values in there, 2 8-bit values. Well, we have ways of doing that. And now we're using a single storage location capable of holding 16 bits, but we're choosing to limit our maximum value to what can be represented in 8 bits, which is 2 to the 8th power if we're talking about signed, or 2 to the 8th power if we're talking about unsigned values, or 2 to the 7th power-ish if we're talking about signed values. And then how do we extract the different values? Okay, we talked about that. Won't talk about things related to networking. We were making a comparison. Won't talk about, this is an operating system kind of slide. Won't test you on that. Won't test you on big endian versus little endian. It's just a design choice. This is more of history. I probably won't ask anything about these. Okay, again, here's like the ARM registers. I'm not going to ask specific things about, you know, what's register 13 used for. That's the stack pointer, for example. And we're going to briefly talk about stacks today as we kind of zip through the last stuff. So I won't ask specifics about these registers, just know what registers are. That'll be good enough, because on the exam, I probably won't have you write any assembly, just because, you know, we had one exercise on that, and it's not all that important for us that we can write it. We really want to be able to appreciate what it is, but I will maybe have at least one question where I give you some assembly and ask you what this does, something like that. So be able to look at 4 or 5 or 6 lines of assembly code and tell me what it's doing in terms of loads and stores and that kind of stuff. So, for example, be able to look at something like this. This is dealing with effectively an if statement where we're comparing R0 and R1. We're branching if R0 is less than R1 to LB max. where we're moving into R2, the value of R1. Then we continue on with the program. Otherwise, we move into R2, the value of R0, and then we branch to LREST and continue on with our program. So this is really showing an if statement. So if I showed you this code and maybe I asked you to, kind of an interesting question. I don't know if it would be if I felt like this would be a good question to ask, but I would only ask it in this format if I thought you would have plenty of time to answer it relative to the other questions I've already asked. Not that it's overly time consuming, but I could say write in a high level language or pseudocode, something else of your choice, the equivalent code to this. So that would be something like, if R0 less than R1, if that's a true statement, then what are we going to do? Set R2 equal to R1. Else, set R2 equal to R0. All right, something like that. So write a high level equivalent of some low level code. Be familiar with some of these instructions. I'm not going to ask you, like what is a very specific instruction used for or something like that. But, the ones that we looked at the most, and we'll look at a couple of new ones today, but they're not earth-shattering things, are like moving things between registers and doing loads and stores between system memory and registers. Again, that relationship between CPUs, system memory, and hard drives. Okay, same thing. This is just kind of the nature of when you're doing a load, you're loading something from memory here into a register. When you're doing a store, you're storing something from a register into a place in memory. Okay, so again, be able to read assembly code. Almost everything of assembly code you look at, like something like this, doesn't really accomplish a whole bunch of stuff, but be able to look through it and tell me kind of what's going on. All right, so certainly things like this, if I have multiple values inside of a register and I say I want to extract the first 4 bits or something like that, be able to do the things with the shifts and the bitwise ands or the bitwise ors to show me the value. So this is where we get into a little bit more mathy stuff. So I would call this slide fairly important. And that's very related to this, where if we're dealing with magnitude, we can use the entire bit space of a register, and that tells us the maximum size value we're dealing with. But if we only want to use part of a register to store a value, well, then we need to know that, and that also then limits the magnitude of the value we can store. The concept of the program counter is important. I would say it's not important that I'm not going to ask you anything about the program counter in ARM versus Intel, where Intel points to the actual next instruction, where ARM points to 2 instructions ahead. Just design choices, kind of unimportant, but we do have this thing called a program counter that gives us an idea of what the next instruction that the CPU is going to deal with is. Concept of memory offsets, we have a base address and then take a step to 3 8-bit steps or something like that off a base address. What's the purpose of that? It's kind of like dealing with collections of things, arrays. Yeah, I won't ask anything specific about cloud computing stuff. It was really showing our small scale hardware register, our hardware architecture being abstracted into a multi-machine hardware architecture where things really haven't changed, but the number of resources we have to work with has increased. Same thing here. The internet connection kind of becomes like the bus between your CPU and your memory. So won't ask anything specific about this kind of stuff, just kind of showing you that cloud computing is effectively a form of computer architecture that lives outside of a single machine. I would say the VR stuff, I'm not going to ask you specific questions about that. We looked at them as examples of they are newfangled mobile devices, just like smartphones, things like that. Okay, so I would say everything from there, that's probably the highlight reel. As we kind of finish the slide set here over the next little bit, I'll point out if there's something that I'm looking at that is, let's call it extra important, but we're not going to be looking at ground, earth-breaking type things today. We're just going to be adding a couple of things to our repertoire, if you will. All right. So any questions about any of that stuff and kind of in terms of kind of what's important for us? If I was going to give actually a generic statement, I would say I'm going to go through and I'm going to assess you on things that are very directly related to mobile computer architecture. Even though we had supporting material that let us put things into context, I'm not going to test you on things that aren't specifically related to the computer architecture aspect of this. So with that in mind, questions before I go on a little bit. Okie dokie. All right, I think we mentioned this just near the end a couple weeks ago. I know we didn't meet last week. We had the R&R day on Wednesday, and Monday I wasn't able to meet, but yeah, Tuesday and Wednesday last week. And for those of you who weren't aware, I suppose I could have emailed about it. I just assumed it was general knowledge, but whatever, that ship has sailed. The university didn't have a spring break this year officially due to COVID, but they did 2 R&R days last Tuesday and Wednesday. They purposely didn't do it on a Monday so that it would discourage people from going home and over a long, an extra long weekend type thing. So the idea is last Tuesday and Wednesday, you were supposed to rest and relax or something like that. Neither of which happened to me those days, but that ship has sailed. All right. So our stack data structure, so this should be something you've already been familiar with in terms of what is a stack. Even if you're just a human being and didn't necessarily have a background in computer science, we have a stack. Think of it like a stack of magazines or a stack of books or, something like that. A stack of napkins. A stack is something when you add something to a stack, you put it onto the top of the stack. When you remove something from a stack, you remove it from the top of the stack. So it's a last in, first out queue. And it supports 2 main functions. We can push things onto the top of the stack and we can pop things off of the top of the stack. All right, pretty simple. This is not earth-shattering type stuff, but what we want to think about as the stack as being this new resource that our computer architecture has available to it. Okay, so up to this point in time, we've had, and it's not really a new resource as much as it is an abstraction of an existing resource. And what I mean by this is we have this relationship between our hardware registers and our system memory. All right. And up to this point, the way we've explored that relationship is through load and store instructions. We can load stuff from memory into a register. We can put stuff from a register back into memory through a store. Okay. Well, now we add a new abstraction to this where there's a part of system memory that's kind of set aside by the architecture to live as the stack. Now, technically, it wouldn't have to live in system memory. It could live in a really large L1 cache or something like that, but that part doesn't necessarily matter. For us, we can just think of there's this abstraction called the system stack. And the system stack, we can say, allows us to very temporarily move values out of hardware registers into a temporary storage location that isn't necessarily going all the way back to memory or normal system memory or even back to disk. Instead, we're kind of setting something aside for a second so that we can probably use it again in a few minutes or even in a few instructions. With the idea that we don't want to give up too much performance, but also what does the stack let us accomplish? So this is probably the most important line that I'm going to say that's related to this. What does the stack actually allow us to accomplish? It allows us to do things that we couldn't necessarily do before because we would run out of registers. All right. In any kind of architecture, we have a limited number of hardware registers available to us. And we can say, oh, well, there's plenty of them. There seem to be 16 or 20 general purpose registers we can work with, which is great. But as our programs get more and more complex, you might start using up those registers and you might need to store values in other places. The stack gives you a convenient place to store those values so that you don't shove everything into hardware registers, making them unavailable for other instructions. Okay, so you can almost think of this as giving you additional phantom registers. Stacks are also heavily used for dealing with functions / procedures, that kind of stuff in assembly code, and we'll look at that here in a few minutes as we just kind of see the use of this tool. So don't put a stack data structure up on too much of a pedestal. It's just an additional resource that we have in our in this system architecture relationship between our CPU and our system memory that says, you don't have to accomplish everything through, let's call loads and stores kind of like these permanent actions or heavy lifting actions. You can toss something over to the side for a second to free up a resource and then bring it back in after you're done using that resource. That's the purpose of this stack. All right, so here's an example. All right, we can move the literal value 2 into R0. Then we can free up R0 by pushing its value onto the top of the stack. Okay, now we can move into R0 the literal value 3. But we've preserved the 2. The 2 isn't overwritten now because we tossed it onto the stack. Then we're going to move a 3 into R0, and we're going to pop off the stack. The top of the stack is our number 2, and we're going to put that into R0, which will actually overwrite that 3. Okay, so we store a 2 in R0, push a 2 onto the top of the stack. Then we overwrite R0 with a 3, and then we overwrite R0 with the 2 that was at the top of the stack. All right, so this just does some back and forth stuff with the stack. Okay, showing us this, we have this convenient magic trick called push and another one called pop that allows us to directly interact with this resource that is provided to us by the architecture called the stack. where we're always operating off the top of the stack. We push stuff onto the top of the stack, we remove stuff off the top of the stack. All right. So you could take a look at this. Here's some example stuff of, you know, when you might use a stack. I think I kind of just explained it out loud pretty well, but feel free to go and look at this this slide on your own. All right, so now this is how functions work. So if we're looking at an assembly language like the ARM-based assembly language, and we want to be able to mimic functions, we've kind of already seen this a little bit, right? Where we've seen how in like Hello World, how those system calls sort of kind of allow us to accomplish functions by like we stage 4 values into 4 different registers, and we call upon the operating system, and the operating system says, which of my functions do you want me to call? And it finds those functions, it looks at that function and says, how many parameters does it need? And then it goes and grabs those parameters specifically from very specific hardware registers. Now, that might be one way of accomplishing this, but we could also accomplish this by saying, oh, the 3 parameters you want are the top 3 things on the stack, for example. All right. So in this code example here, I wouldn't worry about the some of the names of things here. We're dealing with a function. All right. So we have this thing called a frame, which is going to be the thing that actually stores your function. I'm going to call that unimportant for us. All right. So we will, well, here, let me make sure this is a good example. I don't want to spend too much time on this if it's not a super clean example. Let me actually just talk about this at the high level. Okay, so effectively, when we call a function and go and execute a function, what are we doing? We are, if you think about this like in a high level program like Java or something like that, if we make a function call, we are leaving the current part of the program that we're in to go do something else. But ultimately, we're going to be returning to where we left off. So we have to have a mechanism for kind of saving the current state of our program so that we can restore that current state later on when we come back and pick up where we left off. And what's the purpose of that? Well, the idea is that when you go and you move to another label somewhere inside your assembly code, presumably it's going to start overwriting registers. R0, R1, R2, all these registers, these guys are in play now. And any values that you left back there that you were expecting to have later on when you return, yeah, it might not be in the cards because you don't have control over what they're going to change. So this is where that stack can come into play in terms of let's get stuff off of the current registers and preserve them so that later on we can get them back. Now, why does this ultimately end up working? Because you can say, well, what happens if the function that you're calling ends up manipulating the stack? Well, if it destructively manipulates a stack by just popping a whole bunch of values off of it or something, that would be a problem. But the hope would be that whoever wrote the program is writing it to be, well, chances are the assembly code was actually written by a compiler, and the human being wrote some high-level code that they then compiled down to assembly language. But the idea would be is if I'm in the main part of my program and I push 4 values onto the stack, let's say, and then I move over to a function call. And that function call is messing around with registers, whatever it's doing. And it's also messing around with the stack. It's pushing things onto the stack. It's popping things off the stack. The presumption would be when it's done, anything that it put on the stack, it's removed from the stack. So when the program comes back to where I left off, the stack is in the state that I had left it in. Even if the part of the program that went and used that stack continued to work with it. You know, if they added 10 things to that stack, no big deal as long as they popped those 10 things off, which then would give me the ability to just pick up where I left off, because the top of the stack now is what is the same thing as the top of the stack was when I left this. Now, we might have situations where a sub program needs to do more with the stack than that, but we might say a general rule would be that a procedure should always leave the stack in the same condition as when it received it, because there very likely is somebody else relying on what was on that stack. Something along those lines. All right, so this stack data structure gives us a lot of flexibility for adding power tools to our programming languages. We wouldn't be able to have functions without something like this, where we can let another part of the program start executing and not worry about what it's going to do to registers, because we've preserved our values onto the stack, and we just know that when we return, we got to refill our registers back up, which is effectively a context switch, but it's a manual context switch for us, where the context switches we've talked about before dealt with, when this is more of an operating system concept, but when a process runs out of time on the CPU and it has to leave the CPU, it has to pack its bags up. So there's this context switch where all of its current values are preserved in some sort of way, something like that. And they're actually preserved in this thing called a frame, which this references, but I'm not going down to that level of detail for us here. We were just thinking about that stack at the high level. All right, so questions about the stack before we look at the Android Hello World and just see how close it is. Okay, so remember back, we just saw it a few minutes ago as a refresher, that Hello World in Linux Intel based assembly. All right, so now we're looking at Hello World in ARM based assembly for Android, the Android operating system. All right, so up here we have a couple of variables. Here's our hello ARM. So we have a string equal to hello ARM. We have the length of that string. Same two pieces of information we had in Intel. All right, here's the start of our program. What are we doing in our program? Well, we're moving some things into our 0, R1, R2. Now, the order in which we're adding things might be a little different. We're not, instead of AX, BX, CX, we're putting into R0 this number 1, and this number 1 is equal to what? It is relative to standard output. Write this to the screen. All right. How long, or rather, what are we writing? We're going to put what we're writing inside R1. We're going to put the length of what we're writing inside R2. And then instead of AX, so remember with Intel, the thing we did is we moved the thing that we wanted to do, the system call that we were trying to accomplish, we moved that into AX. In this case, for ARM, we move it into R7. All right, so R7, and we can see an interesting connection here. If I just bounce back a couple of slides. Not that one. He wasn't that far back. I just want to make the connection. Because he goes back 75 slides. We had a list of our registers. It wasn't this far back. There we go. Oh, it just lists R7 as a variable register. I thought it was going to maybe connect it to the underlying operating system. So, we have our argument registers R0 to R3, and then our variables R4 to R7. So in this particular case, the Android operating system, when it gets called, it's going to go and check the bucket R7. So it's going to look into R7 and find out, what is it that you want me to do? Now, earlier I said, remember the Linux system call number 4 is syswrite. Okay. Android is based on Linux. So the write system call is also magic trick number 4, system call number 4 on the operating system. All right, so we stage our values in R0, R1, R2. Then we load into R7 what we want to do. This is the cadence of what the Android operating system is going to do when it starts talking to the CPU after it takes over. Okay, then we invoke the system call. So this is us telling Android to go ahead and do their thing. And what's their thing going to do? It's going to jump to R7 and say, what is it that you want me to do? Okay, I require 3 parameters. Where am I writing it? What am I writing? How long is it? And it's going to go do its thing. All right, then we come back here, same thing. So we're putting into R0 the value 0. So like everything worked fine. We're putting into R7 system call number 1, which is system exit. All right, and then we're calling the operating system again. So something I want us to recognize here is we looked at the hello world assembly code that was the output of, let's say, a C program for running on a Intel-based processor. And now we're looking at the hello world assembly code that was written for a, we can assume it was written in C for our example here. And it was compiled targeting still Linux, targeting Android as the operating system, which isn't necessarily guaranteed to be identical to core Linux, but it'll have its own OS flag, but it's still a Linux-based operating system. But this one would be on presumably the Snapdragon architecture, which most of our modern Android devices use. And now we see that, oh, yes, indeed, the program basically looks the same. They've just used a couple of different registers, mostly because Intel and Snapdragon use different register names. Well, that's true. i386 assembly, which talks directly to the Intel processor, uses different register names than ARM assembly, which talks directly to an ARM compliant processor like the Snapdragon. But we ultimately see that the way it's being accomplished, the way these function calls are being accomplished is identical to the way we did it with Hello World for Linux for Intel. All right, so not a whole lot has changed. It was the job of the compiler to make these differences. And this connects those final dots that says, why do, from a question from way, way, way above, why does the compiler need to know about the architecture and the operating system? The answer is so it can do this. It can take your desire in your high level program and turn it into the right collection of magic tricks that ultimately the operating system that's going to call it, along with the architecture on which it's going to be executed, can work together to give you the desired output. Okay, so this is just showing how this program was assembled. If you were doing this for Android, Android comes with a native assembler. Unimportant for us. It's just if you were writing this, there's a tool called an assembler where you can actually give yourself an executable. You would use the assembler if you're trying to be the super geek who's going to write direct assembly code like we just looked at here, as opposed to writing a C program that prints out hello world, then compiling it for Android, which then produces that kind of assembly code. Relatively unimportant for us. Then this shows some examples of if you did this, how would you get it onto an Android device? You use their debugger to push a executable onto a stack that lives on the Android device. Also unimportant for us. This is more of, hey, I just wrote an assembly program. I want to test it on my smartphone. All right. Similarly, if we were doing this inside of iOS, again, showing that the two platforms are very similar to each other, you would accomplish this in a pretty similar way to actually get to the, I don't know if I did an example for, I didn't show an example for iOS, but in any case, I promise you, ultimately the output would be very, very, very similar, with the difference being that maybe inside of R7, instead of the number 4 being loaded, a different value would be loaded, because maybe the iOS operating system, which was, it's still based on Unix, but maybe they're using a different system call number, whether BSD, I think it's OpenBSD Unix is its baseline. I'm not sure what the syswrite system call is in OpenBSD Unix. It very well might be 4. But we could at least say it's plausible that it's not the number 4. So we might see some little differences like that. But at the end of the day, the outputted code for iOS-based Hello World in ARM assembly is going to look a lot like this. Okay, so then the rest of these slides really deal with background information that was, assumed that you had coming into this class. So if any of the things we talked about today, and some of these things we dealt with, along the lines in here, we've done stuff with binary. Here's the ASCII character set, even though we didn't do a lot of things with characters themselves, but computers like numbers, humans like characters. So if we were storing stuff, we would, on a computer, we'd store a number, and then somehow that number would need to get mapped over to a character. Math with binary, again, I'm not testing you on that on here, but it's information that's in here. Our Boolean logic, we see that through the branch instructions, like the one we looked at today was branch if less than. And we also see it for us through our bitwise operation. So here's bit manipulation, bitwise and, bitwise or, and that's from our slides dealing with how do we extract a value from a portion of a register. And then here's our left and right shifts. All right, so you can flip through these things and you might just spend a little bit of time going through some of these background slides just to make sure that you have any information that might be assumed that you have on the exam. But I think I pretty much went through the highlight reel of what I'm going to be pulling from when I do the final exam. So with all that being said, what questions do you have for me? Very talkative bunch early in the morning. Khalib, my coffee's gone cold. All right, if you got nothing for me, that's, let's say, the end of our content. So the next thing that'll happen for us is you'll have your final exam up. It's possible I even put it up as early as tonight, no promises. Depends what time I get back, but probably sometime tomorrow. But it'll guaranteed to be up before 8 a.m. on Wednesday. You can take it, like I said, whenever you want. I need it submitted by midnight on Sunday so that I can get it graded and turn final grades in, because the next 8 weeks classes start next week. So I know several of you are taking 560, the RESTful APIs class with me, which meets at the identical time as this class. So many of us will still be meeting next week. We'll just be meeting on a different, a new topic dealing with RESTful APIs and high-level programming web stuff. So I do need you to submit your exams by midnight on Sunday. But this Wednesday's class, you have that class time to take the exam if you'd like, and you would be able to finish it during the class time. I'll design the exam to take about an hour. Otherwise, time management, you decide what is the best time for you to take it, but sometime before midnight on Sunday. Questions, comments, concerns, bribes? Okay, well, that's what I got for you. I will see many of you soon. Otherwise, we're done for the day. So have a good rest of your week.
Thank you.